In this video, we are going to talk about Cauchy's integral formula and an extension. This is our overview slide, which we'll spend about 5 minutes or less on before we go through each topic in more detail and with more examples. First, we will go over Cauchy's integral formula, which says if f is analytic everywhere inside and on a simple closed contour C taken in the positive orientation, if z naught is any point interior to C, then f evaluated at z naught is equal to 1 over 2 pi I, the closed contour integral C of f of z with respect to dz, z minus z naught. We can also rearrange the terms algebraically to get this form of the Cauchy integral formula. And the striking thing about this formula is the values of f interior to C. So in other words, look at this. We have f at z naught, where z naught is any point interior to our curve. So for our example, if this is C, any point interior to here, the value of f of z is going to be determined by the values of f on the contour. In our video, we will work through this example. Let C be the positively oriented circle. Absolute value of z is equal to 2. So here is our circle of radius 2. Let f of z equals z divided by z minus 3, z plus 3. Then we want to evaluate the closed curve contour of z, 9 minus z squared, z plus I dz. Looking at how we will use the Cauchy integral formula to evaluate this closed contour, we can see we have z over 9 minus z squared. So this portion here is equal to our f of z, which we've noted is analytic inside and on C. No, it's not analytic at z equals 3 and minus 3, but those are points that are outside C, so we're not worried about that. F of z is analytic, and therefore we can use the Cauchy integral formula. And over here, looking at this formula, comparing it to our Cauchy integral formula, we were given f of z, so our z minus z naught, in this case, z naught is equal to minus I, and then we can plug into our formula. And as I mentioned, we will go over this example in more detail. Next, we will look at an extension of the Cauchy integral formula. So we're going to extend it now to derivatives of f at z. So let f be analytic everywhere inside and on a simple closed contour taken in the positive oriented direction. Then here we have f of z is equal to 1 over 2 pi I, integral over c, f of s ds, s minus z. This formula here is essentially the same formula that we have in our original Cauchy integral formula, but because your book derives this formula, they change the z here to the s, and you can tell that z and s are identical because here we're taking it with respect to the variable s, here we're taking it with respect to z. So in this formula, s replaces the z, and then our z naught is replaced with z. Right now we're looking at f at z, whereas over here we're looking at f of z naught. So this is kind of our standard formula, but now we can look at the derivative f prime of z, and we will see that is equal to 1 over 2 pi I, integral over c, f of s, s minus z squared, and then we have our formula for the nth derivative. And we will do these two examples. We'll take a quick preview of the first example, where we want to integrate the closed contour of e to the 2z over z to the 4th dz, where c is the unit circle, z is equal to 1. I'm now going to put this formula here, this integral, into the form, and I'm going to look at the nth derivative, where n can equal to 0, or n can equal to 1, or n can be 2 or something greater. So I have my integral of c, and I want it in the f of s, s minus z to the n plus 1 form. So I want it in this form over here. So I'm going to let f of s, then looking at this, I can let f of s equals e over 2s. In this case, z is equal to 0, and then n will equal to 3. So if I plug these into here, you will see I will get exactly this integral formula here. And from there, I can plug in to my Cauchy integral extension for the third derivative. And again, we will do this example in more detail later in this video. And then we'll have another example here, which is quite straightforward, but we should really go over the material before we go through this one. So that's our review. Let's back up and take a closer look at the Cauchy integral formula. Cauchy's integral formula says if f is analytic everywhere inside and on a simple closed contour C taken in the positive orientation, if z naught is any point interior to C, then we can evaluate f of z naught by doing this closed contour integral 1 over 2 pi I integral over C of f of z over z minus z naught dz. We can also remember this form here, which is simply multiplying both sides of this equation by 2 pi I. I'm going to use this circle here as an example of a closed contour. It's my circle of radius 2, and actually it's in the positive direction, so I should be drawing my circle in the counterclockwise direction. So if f is analytic everywhere inside and on the closed contour C, so it's analytic on the closed contour C as well as inside. Then if z naught is any point interior to C, so z naught, I should just say, is anything in here, right? Not including the boundary, not including C, then we can evaluate f at z naught. So the value of f at any point in here is determined by this integral, 1 over 2 pi, integral on C, the closed contour C, f of z, z minus z naught. So what that implies, the values of f interior to C are completely determined by the values of f on C. It's the idea that what happens in the interior of the circle is completely determined by the boundary of the circle. So let's try an example. I have my Cauchy integral over here for your reference, and our example is let C be the positively oriented circle, absolute value of z equals 2. That's our circle of radius 2. And let f of z equals z divided by 3 minus z times 3 plus z. And I rewrote it here because I like looking at it this way. We want to evaluate the integral over c of z divided by 9 minus z squared, z plus I dz. And the first thing we should note is f of z that's been given to us is analytic inside and on C. We see that there are two singularities, that is z equals 3 and z equals minus 3, but those 2 points are outside of C. So we're good now. We're analytic inside and on C. We can use Cauchy's integral formula. The other thing to note is when we want to evaluate this integral, we have z over 9 minus z squared. That's simply f of z, right? If we multiply out the denominator, we get z over 9 minus z squared. So this is f of z, and then we have our 1 over z plus I, which is exactly the form that we need in our Cauchy integral. We have f of z on top and z minus z naught on bottom. In this case, then, z naught is equal to minus I. In other words, if I just take this formula down here, I'm just going to plug in, so I have f of z naught, and in this case again, z naught is minus I, is equal to 1 over 2 pi I, and then I have my integral over C. F of z is z over 3 minus z, 3 plus z, and then I have z minus z naught, which is what gives me my z plus I. You can see that this formula here is exactly the problem that I'm asked to solve. Well, except that the 2 pi I needs to get multiplied over. So now by Cauchy, I have my f of negative I times 2 pi I is equal to my integral. So now my integral is equal to 2 pi I times f of negative I. So I plug in negative I into f, and I get negative I. 3 minus negative I gives me my 3 plus I. Here my 3 minus I gets brought down, and that will give me pi over 5, and that will be equal to my integral. that's the Cauchy integral formula. It gives you a quick way of evaluating these path integrals, these closed curve integrals, just by plugging in the value f of z naught, some point interior. Next, we'll talk about an extension of the Cauchy integral where we extend the formula to apply to derivatives of f at a point z. So here we have the extension. It's an integral representation over here for derivatives like f prime of z. We have the same condition that f must be analytic everywhere inside and on a simple closed contour C taken in the positive orientation. This is our Cauchy integral formula. Now we have a formula for f prime of z based on the integral, and you see it's the same formula except now we have s minus z squared. And the nth derivative, we have the n factorial here, and we have s minus z n plus 1. These formulas are derived in your book, so I did not do the derivation here, but we're just going to do examples and learn how to use this formula. Another thing to comment on when we talked about the Cauchy integral formula, we had this in terms of z as our variable of integration. So this was f of z dz, and then we had z, and instead of z here, we had z naught. And I have the Cauchy integral formula here pasted just for your reference. Again, we substitute z for z naught, and then we substitute s for z. So if I want to write this extension kind of in the form of the original Cauchy integral formula, which by the way, a lot of the examples are written in this form, I could say if f of z is analytic inside and on C and z naught is interior to C, then our derivative at z naught is equal to 1 over 2 pi I C f of z dz over z minus z naught squared. So this is just this formula again with the z's replaced with z naught and the s's replaced with z. My nth derivative of f evaluated at z naught is equal to n factorial over 2 pi I integral over the curve C f of z z minus z naught n plus 1 dz. And this is probably the form that you should write down or remember just because so many examples are in this form. But in my overview slide, I wrote it in this f of s form because that is the formula that was in your book when your book derived the formula. Now we can do an example. I have the Cauchy integral formula as well as the derivative extensions here for your reference. And the problem is to evaluate the closed contour integral of e to the 2z divided by z to the 4th dz, where c is the unit circle of radius 1. Now I want to work on putting this closed curve integral into the form that I have in my Cauchy formula. So I want to put it in this form here, and I chose this f to the n as opposed to the f prime because I have a z to the 4th power. Here I would just have a z to the 2nd power, so in this case I want n to equal to 3 so I can get z to the 4th power. But actually, let me back up a little bit. Remember this here, the variable is s, so I want s to the 4th power. So again, I want this into this form. I'm going to start by copying this form over here. And then looking at what I have here, I'm going to write my exp to z. I'm going to let that be my f of s. So f of s is equal to e to the 2s. Then down here, I have my s. Remember, s is my variable now. And I'm going to subtract, I'm going to let my z, not this z, but this z over here, where this is the point interior, equal to 0. And then n is going to equal to 3. So I'm going to plug these numbers into here. What I get is my f of s is my e to the 2s, s minus z, that's s minus 0, raised to the n plus 1, that's 3 plus 1 is 4, ds. And you can see now I have my closed curve integral in this form with my f of s identified as e to the 2s, my z, which is the point interior to the circle, as 0, and in n equals 3. Using my Cauchy integral formula, this integral using this formula up here, is equal to the fn of z times, and I'm just going to move this to the other side, 2 pi I over n factorial, which then, just plugging in n equals 3, so the third derivative evaluated at z, and again here z is 0, evaluated at 0, 2 pi I over n factorial, this should be 3 factorial. Now getting the third derivative of f, so f of s is equal to e to the 2s, f prime of s is equal to 2 e to the 2s, f double prime is 4 e to the 2s, and triple prime is 8 e to the 2s. Evaluated at 0 and then multiplied by 2 pi I over 3 factorial will give me my final result that my closed curve integral is equal to 8 pi I over 3. This next example is to let z0 be any point interior to a positively oriented simple closed contour C. Use f of z equals 1 to show that the closed contour integral of 1 over z minus z0 dz is equal to 2 pi I. For this problem, I decided to use this other form of the Cauchy equations, the one where my variable is now z and the point interior is z0. Again, this is the same formula as what we have up here, except the s's are replaced with z's, and my z is replaced with z0. And you really can use either formula, but this is probably more convenient. And since I did the last example using this formula, I figured I'd do this example using this more convenient form. Now I want to put my closed curve integral here into the form of my Cauchy integral formula. I've moved my closed form integral here, and I put the dz over here just because it looks nicer to me. So I can see that on the bottom, my power is just equal to 1. So in this case, n is equal to 0. They tell me to use f of z equals 1. Now when I plug these numbers into my Cauchy-Riemann equation, I have f of z naught. So the 0th derivative is just f, and then my z naught is equal to, here my n is equal to 0, so that's 0 factorial, which is just equal to 1 over 2 pi I. My closed curve integral, my f of z is 1, and then my z minus z naught stays here, and then my n plus 1 will, n is equal to 0. And what that gives me, so I'm going to isolate the integral I'm interested in, so I move this 1 over 2 pi I to the other side, so I have 2 pi I, and again the 0 factorial is just 1, so 2 pi I times f at z naught. But since f of z is just equal to 1 at all points, that means my closed curve integral is equal to 2 pi I times 1, which is just 2 pi I. So I have proven that this closed curve integral is equal to 2 pi I. To review what we have covered in this video, we looked at Cauchy's integral formula that gave us a way of evaluating f of z naught, or we could think of it as giving us a way of evaluating the integral over a closed contour of f of z dz over z minus z naught. So if f is analytic everywhere inside and on a simple closed contour C, taken in the positive orientation, if z naught is any point interior to C, then f evaluated at z naught is equal to 1 over 2 pi I integral over C of f of z over z minus z naught dz. Or we can say by multiplying both sides of the equation by 2 pi I that the closed contour integral of f of z over z minus z naught dz is equal to 2 pi I f of z naught. And the surprising thing is this says that the value of f interior to C are completely determined by the values of f on C. So it's the idea that what happens inside is completely determined by what's happening on the boundary. And we did this example here. Let C be the positively oriented circle, absolute value of z equals 2, and let f of z equal z over 3 minus z times 3 plus z, and we evaluated this integral over C, z over 9 minus z squared, z plus I. First, we took this integral and we got it into our Cauchy form. So we let z equal to z over z over 3 minus z, 3 plus z, which is exactly this 9 minus z squared. And then our z minus z naught is our z plus I. So z naught is equal to negative I. So once we have our f of z identified and our z naught identified, we can simply plug into our formula. So our integral is equal to our 2 pi I f of negative I, which is equal to pi over 5. The next thing we did was an extension of the Cauchy integral formula. So we looked at how to evaluate derivatives of f at a point z that's inside the simple closed contour. And we had this integral representation of that. So here's our regular Cauchy integral formula. And then for our derivative, f prime of z, we have that equal to 1 over 2 pi I integral over c f of s minus z squared. And for the nth derivative evaluated at z naught, we have n factorial over 2 pi I integral over c f of s ds s minus z n plus 1. And one thing I did mention, your book went from using z over here, these formulas, where z is the variable, to making s the variable here. And then our z naught was our interior point. And over here, our z was the interior point. You know, if that bothers you, you can rewrite this formula, in which case you would have f of z naught equals 1 over 2 pi I f of z dz z minus z naught. And here you would put in z naughts wherever you see a z, and you'd put a z wherever you see an s. You could just rewrite the formulas so they look consistent. Or you can just remember that this is the variable of integration and that here z is the point interior. Well, we did this example here where we evaluated the closed contour c integral of e to the 2z over z to the 4th. And we used the Cauchy integral formula for the nth derivative. We let f of s equal e to the 2s. We set z equal to 0, since this is z minus, basically z to the 4th, it's not z minus any number, so 0. And then n is equal to 3, since the power on the bottom is n plus 1. So when we plug in f of s equals 2s, z equals 0, and n equals 3 into this part of the formula, which we made put it in this Cauchy form, then we get f, the third derivative of f evaluated at 0 is equal to 3 factorial 2 pi I integral over c e to the 2s over s to the 4th ds. We multiply both sides of the equation by 2 pi I over 3 factorial, and we separate out our integral is equal to f, the third derivative of f evaluated at 0, 2 pi I over 3. We evaluated the derivative, did some algebra, and our final answer was 8 pi I over 3. We did this one additional example, which I won't repeat in this review, but you can go back and look at it. And that is it for this video. Thank you for watching.